Hey guys, welcome to Chem 20. This first unit, actually the first two units are both really short. And in this first unit, we're gonna start kind of like the first half of this unit will all just be review of grade 10 stuff that you need to know that we're just gonna kind of go through really quickly. And today's lesson, we're gonna be focusing on how to name ionic compounds. So when it comes to naming ionic compounds, you do have to know how to go both from name to formula as well as formula to name. When it comes to writing the formula, knowing the number of valence electrons, knowing the number of charges are both really important because you have to cross over your charges and stuff like that. And then you do have to know kind of some of the different rules for different types of ionic compounds, including our multivalent metals and our polyatomic ions. So just a reminder, an ionic compound is formed when you have a metal and a non-metal bond to one another. The metal is always going to lose electrons, so it becomes positive, so we call it a cation. The non-metal always gains electrons, becoming negative, so we call it an anion. And then the opposite charges of the cation and anion attract one another, which is how the ionic compound actually bonds. The charge of the ions depends on how many electrons are lost and gained, which is dependent on the number of valence electrons that the atom had originally. So valence electrons are just the electrons in the outermost shell of an atom. And the number of valence electrons determines how many bonding sites an atom has. So just a reminder, generally speaking, you draw your valence electrons like top, bottom, side, side, and then repeat in those positions, and only lone electrons are able to form a bond. Atoms are most stable when they have a full outer shell. So that's the octet rule, meaning that most elements are most stable with 8 valence electrons, though for elements 1 through 5, 2 valence electrons is a full outer shell for them. So there is a pattern to valence electrons. As you move across the periodic table, the number of valence electrons goes up. So in the first row, you have 1 valence electron. So everything in the first column is going to have 1 valence electron. Everything in the second column will have 2 valence electrons. Then if you skip the transition metals, the dropped down section, and go over to the 13th column, that's going to have 3 valence electrons, then 4, 5, 6, 7. And by the time you get to the last column, you have 8 valence electrons. And the number of valence electrons is going to determine how many electrons are going to be gained or lost. So anything with 1 valence electron will always lose that valence electron to become an ion. It will end up as a +1 ion. Anything with 2 valence electrons will lose those 2 and become +2. Anything with 3 valence electrons will lose 3 and become +3. And then by the time we get to column 14, which has 4 valence electrons, this is where the atoms are going to start gaining electrons instead. So something with 4 valence electrons will gain 4 more electrons and become -4. Something with 5 valence electrons will gain 3 and get a charge of -3. Something with 6 valence electrons will gain 2 and become -2. Something with 7 will gain 1 and become -1. And if it already has 8 valence electrons, it has that perfect octet. It is not going to gain or lose any electrons, so it will have a charge of 0. And again, this is all about trying to get to that perfect octet where it's most stable. So for instance, if in that 15th column there, something already has 5 electrons, if it gains 3 more, now it has 8, so it has that octet. Same with like 6 plus 2 is going to be 8. In the other columns where it's losing electrons, it's trying to get rid of all the electrons that it has in its valence shell so that it goes down to the next valence shell or the next orbital, which will then be full. Okay, so that is just kind of something that you need to memorize in terms of the periodic table. Okay, so if we look at the periodic table over here, again, you just need to memorize that as far as valence electrons go, anything in this column is going to have 1, 2, 3, 4, 5, 6, 7, 8. And as far as charges go, it'll be +1, +2, sorry, +3, -4, -2. Sorry. +1, +2, +3, -4, -3, -2, -1, and 0. You'll notice that for both valence electrons and charges, I have skipped this lower down section here. That's because there's no rule to determine what the charge of those metals down here are going to be. So the transition metals, which again, we don't always know the charges of, are anything starting in this column right here, all the way across and then down underneath the staircase over here. So it's pretty much everything under the staircase, not including aluminum, which is above this line right here, and all the way over to the third column. Okay, so in terms of the formulas for ionic binary compounds meaning that they only have 2 different types of elements in them. This is when you essentially just write the symbol for both of the elements, write the charge, cross over your charges, and then simplify. So let's go through an example of what this would look like. So for example, if I had, let's say, magnesium nitride. I would start by writing the symbol for magnesium and for nitrogen. I'm then going to write the charges of each. So magnesium is in the second column, so it will have a charge of +2 or 2+. Nitrogen being in the 15th column is going to be -3 or 3-. I am then going to take those charges and cross them over. When I cross them over, you only write the number, you don't write the positive or negative sign. So that would be Mg3 N2, like so. And then you just want to make sure that it's simplified. So if there's any 1s, we get rid of them, we just don't bother writing them in. And if these numbers are the same or are a multiple of one another, that also means that they can be reduced because 3 and 2 are not the same and they're also not a multiple of one another, meaning that I can't divide 3 by 2 and get a whole number, or 2 by 3 and get a whole number. That means this is already simplified. Let's try another example where you would need to simplify. So if we had, let's say, calcium oxide. Calcium is Ca, oxygen is O. Calcium has a charge of +2, oxygen -2. When we cross those charges, we end up with Ca2O2. Now, 2 and 2 are obviously the same as each other, so they can just cancel out. Another way of thinking of that is that we divide them both by 2, which would leave us with 1s, and we don't bother writing in any 1s. So our final answer would be CaO. Of course, we need to know how to do this process backwards. So if we are given the formula, we need to know how to get the name. In order to do that, you always write the name of the metal, then the non-metal, and just change the ending to IDE. There are no prefixes that would be used in this process. So for example, CaCl2 is just calcium chloride. Pause for a second and see if you can figure out what MgI2 would be. That one, we just write magnesium and then iodine, change the ending to IDE, so it would be magnesium iodide. Okay, it does get a little bit trickier when it comes to our multivalent metals. Multivalent metals are metals that exist in this transition metal zone, so in this dropped down area and all under the staircase. Some of those transition metals can have more than one possible charge, and if that's the case, we call them multivalent metals. Once again, if we are going to be writing the formula for multivalent metals, we just write the metals formula and the nonmetals formula, cross over their charges, and simplify it. The only difference is that in this case, because we don't just know the charge by where the metal is on the periodic table, the charge of the metal is actually written in Roman numerals. So let's look at an example of this. So for example, I might have iron 3 oxide. And in this case, this 3, this Roman numeral, is the charge of the metal. It's always the charge of the metal. So we're going to start by writing our symbols for iron and oxide, or oxygen. So iron is Fe, that is one that you have to have memorized. Oxygen is O. Then we're going to write the charges. So this is a 3 in Roman numerals. That means our iron has a charge of +3. And then oxygen, that's just one of our normal elements. It always has a charge of -2 because it's in the 16th column. Then we, of course, take our charges and cross them over, which gives us Fe2O3. Okay. In the example here that I've asked you to try, I said try lead 4 sulfide. You'll see that I've miswritten the symbol for 4 in Roman numerals, and that's because my first year teaching this, a lot of my students didn't know what 4 in Roman numerals looked like. So if you do want to write it like this, that's fine if you just don't know what 4 in Roman numerals looks like. But just so you know, if you see it on a test or in the textbook, this is what 4 in Roman numerals actually looks like. So with that said, lead 4 sulfide, figure out how you would write that as a formula. Pause here, come back for the answer. So the correct answer would be that you would have lead, which is Pb. It would have a charge of +4. Metals charges are always positive. Sulfur, just because of where it is on the periodic table, has a charge of -2. We would cross those over and get Pb2S4. But then, of course, we do need to simplify this. And because 2 and 4 are multiples of one another, this can be simplified. All we would do is divide both sides by the smaller of the two numbers. 2 divided by 2 is just 1, which we don't bother writing in. And then 4 divided by 2 is, of course, 2. So your final answer would be PbS2. Now, it's actually even trickier to go the opposite way when dealing with multivalent metals, so to go from the formula to the name. And that's because, just like with ionic compounds, we're going to write the metal, we're going to write the non-metal, and we're going to change the ending to IDE. But in the case of our multivalent metals, we have to write in the charge of the metal in Roman numerals. So you've got to figure out what that charge is. And the way we do that is by something called reverse crossing over. So let's go through some examples of what reverse crossing over looks like. This is how we determine the charge of our multivalent metal. So when you do this, your first step is to write the charge of the non-metal. That's the thing that we know the charge of just based on where it is on the periodic table. Then you work backwards using reverse crossing over and proportional reasoning to figure out what the charge of your metal is. And then, of course, writing that in Roman numerals. So I know that probably doesn't make a lot of sense without actually going through some examples. So let's do that. So for this example, I am going to do PbO2. And you need to figure out what the name of this is. So our first step is to just say, okay, Pb is lead. Because of where it is on the periodic table, it's right here. So it's underneath the staircase in this kind of dropped down section. That means it is multivalent, or it could be, it is multivalent. So we're going to need to put its charge in Roman numerals. And then O is obviously oxygen, and we change the ending to IDE, so it is oxide. But then we have to figure out what is that Roman numeral going to be. And to do that, we use our reverse crossing over. So I'm going to go off to the side over here. And I'm just going to write this, but like separated. And then I'm going to write in the charge of the oxygen. That's the one that I know the charge of. I'm trying to figure out what the charge of the lead is. So I'm going to kind of cross over this charge here, the charge that I know, and it should give me a 2 right behind the lead. But you'll see there isn't a 2 there. That means that something canceled out this 2 and left nothing behind. So essentially what that's telling me is that something divided that 2 away. That means that I also, on this other side, must have had something that got divided by 2 and left me with that 2. So what I'm really saying here is what divided by 2 would still leave me with a 2. And of course, the answer to that would have been 4. A 4 divided by a 2 would leave me with a 2. That means that this charge must have been a positive 4. So I write that in as Roman numerals. Let's try another example, because I know this is tricky. So next step, I'm going to have FeN for my second example here. Fe is, of course, iron. We don't know what its charge is, and then N is nitrogen, and we change the ending to IDE. I'm then going to go over to the side and separate those. I know that nitrogen has a charge of -3. I don't know what iron's charge is. So I'm going to cross over the charge that I know, which is a 3. So that means that I should have a 3 behind my iron, but I don't. So something canceled it out and left nothing behind. The only thing that would do that is a 3, which means that whatever was on the other side that got crossed over from the iron also got divided by a 3. And what divided by 3 would leave nothing behind? Well, of course, that would be another 3. So X must have also been a 3 that got crossed over from the iron. So iron 3 nitride would be your final answer. Pause here and try these two at the bottom here. Okay, so with CuF, that is copper something fluoride. So we start with our fluorine. That has a charge of -1, which would cross over and leave a 1 behind the copper. There's nothing there. That's normal. We don't bother writing in a 1, which means that copper must have also had a 1 because nothing is being canceled out here. We are just not writing in our 1s. So this must be copper 1 fluoride. If we look at CuF2, it's still copper something fluoride. We still have fluorine with a charge of 1, that we're going to write in there. But this time, we have a 2 behind the fluorine. And because in this case, nothing got canceled out, this was only a 1 to start off with. So if we divide that by 1, we're still left with 1, which we just don't bother writing in. That means that this 2 must actually be the charge of copper in this case. So our answer this time would be copper 2 fluoride. The one other type of ionic compound that you are going to have to deal with this year is something called a polyatomic ion. This is when you have more than one element in an ion. And in that case, you're still going to have a single metal ion, so you'll start by writing its name, and then the polyatomic ion is going to be an ion made up of more than one non-metal. Each polyatomic ion has a unique name based on the non-oxygen element and the charge and the number of oxygens. You are going to have to memorize those in Unit 3. But at this point, don't worry about naming your polyatomic ions. If you see a polyatomic ion, you do have to know how to like deal with that in terms of like balancing chemical equations, but feel free to just like look up what your polyatomic ions look like what their formulas are, if they happen to come up on a worksheet or something like that. We're not going to get into the polyatomic ions until Unit 3. But just so you can recognize them, what a polyatomic ion looks like would be something like if I had CaNO3, something like this. This is a calcium ion and a nitrate ion. And because calcium has a charge of +2, that has crossed over. That is where this 2 here comes from. And because there's nothing behind the calcium that has crossed over there, that tells us that our polyatomic ion has a charge of -1. So you are going to have to be able to do this kind of things. You're not, at this point, going to have to tell me that this is calcium nitrate. Just to kind of go over another example here, if we had, let's say, AlPO4. This is aluminum phosphate. We know that aluminum normally has a charge of +3, which would cross over here. But because there's not a little 3 here, it must have gotten canceled out. And that is because both aluminum and phosphate have charges of 3. Okay. Anyway, that's it for today's lesson. The trickiest part of this is probably going to be doing your reverse crossing over to figure out what the charges of your multivalent metals are. So just make sure that you're practicing that. Also, in terms of what elements to memorize, you do need to memorize, and I will write this down for you. Essentially all of elements 1 through 20. So if you look at the atomic numbers on your periodic table, so like 1, and then helium is number 2, 3, 4, all the way through until calcium is number 20. You need to memorize all of those. You also need to know iron, which is Fe, nickel, which is Ni, zinc, which is Zn, bromine, which is Br, Ag, which is silver, Ba, which is barium, Au, which is gold, Hg is mercury, Pb is lead, I is iodine, and yeah, that's it. You might, again, on a worksheet, come across something referencing like strontium or cesium or something like that, might not hurt to know what cesium is either, actually. So yes. So you might see some of those referenced on a worksheet. If you do and you just don't know what they are, look them up. But on a test or a quiz, these are the only elements whose names you need to have memorized. You don't need to memorize their atomic number. You don't need to memorize their atomic mass. Just be able to match symbol to name. Okay, that's it for today's lesson. Let me know if you have any questions.